Hello, my name is Cuman Blake. I'm going to be teaching a class on high precision analog, dealing with amplifiers, printed circuit board design, etc. This class is for those that are interested in the analog content. You need some experience previously designing analog circuits so that you can follow along. As an overview, we're going to cover precision op-amp topics. So we're talking about microvolts of error, picoamps error, that type of thing. We're going to show some circuits that implement that level of precision, and I'm going to give some tips and tricks on how to do that in a practical design. The class abstract is here for you to read. You can also read that in your PDF file that you received along with this class. Basically, it says what I just said. It also gives some information such as we're going to talk about more modern design rather than some of the traditional design that you'll see in college textbooks. So to start, here's the agenda. I'm going to talk about high precision circuits to start. And so I'm going to talk about voltage errors, current errors, and the parts that go with that. But that's only a piece of the design, and it's actually the easier piece of the design. So once that we've covered that, I'll move over and start talking about printed circuit board design and tricks, tips and tricks. That is where a design is either made or broken, is at that point. So we'll talk about how to do that on a printed circuit board, and then I'll summarize. Before we get into the actual class, I'd like to also mention that the PDF file that goes with this class has speaker notes, and it also has extensive appendices that you can go for further information or other ideas that are not covered in this class. This class simply can't cover everything that you may need. And this slide talks a little bit about that. There are some references to different data sheets, application notes, available boards. Talk about comparison of effects. I talk about potential problems in this class. How big are those problems? Does it cause a millivolt error? Does it cause 10 microvolt error? This will tell you that, at least at a high level. And then there's some very detailed information on some of the circuits in the back. So let's start. Let's start with the high precision circuits that deal with voltage errors. So to begin, we need to talk about different types of sensors. Here we talk about temperature sensors. You might get an integrated silicon sensor from a vendor, and they may give you like 2 millivolts per degree C resolution. That's fairly easy to measure. That's fairly easy to deal with. That's an everyday design. But if you chose instead, say, this RTD, you're going to find that your resolution is going to be on the order of 5 microvolts, or 4 or 5 microvolts, somewhere in there. Actually, and that's for 1/100th of a degree C. So that's going to be a laboratory grade RTD. That's really tight. We'll talk about that. That's going to be a tough design. Another common sensor would be Wheatstone bridges used in strain gauges and pressure gauges. Again, depends on what you're doing. Some pressure gauges may have very high resolution where maybe a strain gauge would have a low resolution. So it just depends on your sensor. Another theme that's going to be covered in this class is the fact that there's a big difference between the traditional analog design and the modern design. When I started my career, I used to help customers design circuits that had 4 to 10 op-amps in them. Today I can't do that. Most of my customers tell me they can do 1 op-amp in their design, maybe 2, and that's it. That's all their boss will let them put in. And most of it has to be done in digital. So I'm going to talk about ways that that is done. The correction methods, ratiometric circuits, mixed signal circuits rather than pure analog. So let's talk about one potential circuit. I have this amplifier here that is a very heavy driver. It'll output 100 milliamps of current, but its offset is not good. It's pretty high, and if you want low offset, you might combine it with this op amp here, which by the way is an auto zeroed op amp that helps correct the offset voltage. So here's a way of using a couple of op amps to get the best of both. And all these resistors, capacitors are just basically a feedback circuit. This amplifier is configured as a Miller integrator, which is fed into that, and it senses the voltage between these two pins and corrects it via the feedback loop. Another solution that you might see would say we have this Wheatstone bridge, some kind of sensor, let's say strain gauge, and it's very popular today to take a delta sigma converter and measure the difference voltage across here. There's a lot to be said for this. It reduces the number of components on your bill of materials. The drawback is this is going to be a much higher resolution converter and therefore possibly more expensive and more difficult to design the printed circuit board. The only other comment I have at this point is these capacitors filter any noise you see here. The reason for this capacitor here is to swamp any mismatch between these two capacitors. If they're not the same value, you're going to get different pulls on these two legs, and therefore you'll get a common mode to differential mode conversion, which can be a problem with very noisy environments. Well, what if we decide to do a slightly different approach? I've seen this circuit in the literature. It's not my favorite, but it does work in some conditions. Instead of doing a fancy del-sig converter, they throw an amplifier in first, so you can get a cheaper amplifier and a cheaper converter at the price of more real estate on your board. And you only need a single op amp to do this. The problem is, if you look here, you're looking into a high impedance, and here you're looking into this low resistance. So you don't have a symmetrical load on the bridge, and therefore this causes a common mode to differential mode problem. And again, that's going to cause you trouble in your application if you have a lot of noise. So this circuit is actually intended for fairly quiet environments. I'm sorry about that. Somehow my computer thought I was going faster than I am. I'll try to work with my computer a little better. So here's another, so here's the one we just talked about. Here's a more traditional one with a little twist. You take this bridge sensor, you filter it, and then you have this input stage to the traditional 3 op amp instrumentation amplifier. You can go in many textbooks and find this. Basically, this stage sets a high differential gain, a gain of about 100 here. And then the output, the difference at the output is sensed by this del-sig converter and sent to the microcontroller. The advantage of this circuit is it's very symmetrical, it's very high performance. The converter doesn't need to be as high resolution, but it is a little more complex. Later on in this class, I'll explain why I have 2 resistors here rather than the traditional 1 resistor connecting those 2 inputs. There's a practical reason that relates to printed circuit board behavior. So here's a 4th solution. I can obtain, instead of an op amp, I can use an instrumentation amplifier to sense this differentially. This instrumentation amplifier rejects the common mode noise, amplifies it, and sends it to the converter. So depending on your application, one of these particular circuits may help, or it may give you an idea of something you can try for your your target application. So let's talk about something that's usually a little more precise, which is RTDs. If you haven't used RTDs in the past, you may or may not be aware that they have 2-wire, 3-wire, or 4-wire configurations. I'm showing a 3-wire configuration. Here's the actual RTD, and then you have wiring resistance on each one of these legs. So this circuit is a very simple, very cheap way of measuring the voltage drop across the RTD, which, by the way, you have this voltage reference. The current flows through and drops a voltage here. Notice this is a ratiometric circuit. The voltage here is proportional to VDD. So why do I have 3 legs here? Because I can do this switch. I can measure here, I can measure here, and then the Del-Sig converter with its minus input will differentially reference everything to this input here, which is basically an open circuit. So therefore it'll measure this voltage, and this leg will get a voltage drop. So this is a way that you can, in firmware, correct for the wiring resistance drops. We see basically the same application, but again with this different input stage that we saw previously. The 2 op amps at the beginning of the traditional 3 op amp instrumentation amplifier. And then over here, this Del-Sig converter, because it senses differentially, replaces the traditional differential amplifier at the output. And by the way, we do sell more than PIC micros. These slides were put together just before we acquired Atmel, just as a comment. We're not excluding them from the list here. Thermocouple. Here's another application. We're going to actually talk a lot about thermocouples in this class, so this is a good introduction. Thermocouples have what they call the hot junction and the cold junction. Basically, in order to correctly estimate the temperature here, you have to know the temperature on this side. And so in this design, I've put a silicon IC type of temperature sensor that outputs a voltage, and it gets a gain of 1 to the output. This thermocouple, it does not have great sensitivity, so we need a lot of gain. So its gain is 400, that's about a gain of 25, or 250, I'm sorry, about a gain of 250. And we filter it at the output. So this is a way of summing this voltage and this correction voltage that is due to this temperature and getting the corrected output at there. Just as a comment, not everyone may be aware of this, but with this circuit, you can put multiple differential inputs into this difference amplifier by just putting 2 more resistors, and it's just simply the ratio of these resistors set the gain for each individual leg. It's not more complicated than that. So we've kind of gone through a few circuits fairly quick. They've shown the more modern approach where we try to reduce the number of amplifiers. But now I'd like to do a little demonstration, because after all engineers are pyromaniacs at heart. In other words, we like to play with fire. And so I'm going to actually do that. We have here a printed circuit board where we implemented that thermocouple design. And it's a type K thermocouple. I have a thermocouple wire that's 1 meter long. It's kind of coiled up like a spring. And so if I take out my cigarette lighter and I heat the end, something's going to happen. Well, let's see, this is still running. So what I have here is a display what's going on. This has been quietly running in the background, and you'll see that here's the hot junction temperature, and the scale is between -100 and 1,000 degrees C. And the blue trace is the cold junction temperature, which is measured right here on the board, right at the jack. So you'll see that I put the cigarette lighter on and something happened. You'll notice that it went up and spiked down. It went up a couple of hundred degrees C, and the cold junction also went up a little bit. So let me try it again and try to get it much hotter. Okay, I got it up to a little over 500 degrees C that time. So that's pretty warm. You'll notice again, it goes up quick and then it slowly decays, basically a single time constant decay. And you'll notice that the cold junction temperature went up. Well, why would the cold junction temperature go up? Because I'm heating the thermocouple. Why would that temperature change? Well, if you think about it, this is a wire, a metal wire, and that heat that I applied at this end conducted through the wire to the board and changed the temperature of the board. This is going to be very important later on in our class. You'll also notice that you have a fairly slow time constant on this decay after I take the heat off, and that's due to the time constants of the board, the thermal time constants. We'll also talk about that. The other thing I can do is I can get out this freeze spray can and make it go cold. More than that. How about that? So it went down to, I'm estimating, minus 50 degrees C at this end. So everything works out nice. Theory matches reality. But there are a couple of anomalies, right? The anomaly of why this temperature goes up after I hit it with heat on the end. We've explained that. But why does it take so long to decay? If you have any questions or if you would like to play with the circuit, this board is actually available from Microchip to be purchased. And in the references section of the PDF you receive, it has a reference to that board. Let's change gears again. Let's talk about low current errors. For some people, depends on what you're doing. I've known people that 1 amp was a low error. I'm used to signal processing, so I usually talk about anything below, say, a nanoamp as being a low current. And to start this discussion, I'm going to show a circuit that we could use here at Microchip. Matter of fact, this is actually very similar to a circuit we use to measure the bias currents on our amplifier products. I thought it'd be kind of fun for you to see this. So this basically is what's called the transimpedance amplifier. That's because our signal at the input is a current and it puts a voltage out. So voltage divided by current is impedance, and it's trans because it goes across the amplifier. It's a simple design. There are a couple of gotchas that if you haven't done this kind of design before, you may not know how to handle them. One is that the input capacitance here at the op amp will destabilize the circuit unless I put a compensating capacitor here across the feedback resistor. In many cases, it's a requirement. It just depends on the combinations of capacitors, resistors, gain bandwidth product of the op amp, whatnot. But keep that in mind. There's a good chance you'll need a capacitor to stabilize the circuit. The other thing that may not be obvious is it's probably wise to have a resistor here. Not that you'll really drop much voltage across it, but it's there so that when I connect and disconnect my devices under test, I don't get a shock that damages the circuit. So other than that, this is pretty straightforward. Have a leakage current going in the op amp, goes through this circuit. This is a very large resistor, and then these two resistors set at a high gain, and I measure a voltage out, which represents the current at the input. Well, we're next going to go to an implementation where I take out this resistor. So let's go back and look at the previous circuit and talk a little bit about that resistor. the major problem with this resistor is the thermal noise. The thermal noise dominates the noise errors in the circuit by a wide margin. Therefore, it's really nice to take that resistor out, and that's all this circuit does. It takes out the resistor, leaves the capacitor there, and then you put in the switch so that you can initialize the circuit. And then once you open the switch, if you'll think back to your theory from college, the constant current going into a capacitor is going to cause a waveform that looks like a ramp. It's going to go up at a constant rate. So instead of measuring a voltage out, you now measure how fast the voltage changes with time. And usually you'll measure once, and then so many seconds or milliseconds or whatever later, you'll measure again, and the difference in voltage is proportional to current. And it's much, much lower noise. I have a couple of plots here that show this. Here's the noise error, and here's the measured current. You'll notice that the Miller integrator does better than the transimpedance application. After averaging, they both get the same noise. But that's not where it's really interesting. What's interesting is if I plot my current here, and then I plot the amount of time it takes to measure at the accuracy level I want, you'll all of a sudden see that after averaging, the transimpedance amplifier is way up here in the red curve, and the Miller integrator is here in this golden colored curve. So down here, there are more than 2 decades difference between the times. That's huge. And as current goes up, it becomes less, but it's still about a decade difference at the top. So doing this gives you a huge advantage in measurement. This is an idea that you may want to consider if you're doing this kind of application for yourself. Let's talk about some precision parts, just to talk about what's out there. Some of them you may not think of as precision parts, but they play a major role there. I'll talk about that. First of all, I'd like to talk about zero drift op amps. These have been around a long time. The original implementation of this kind of amplifier was done with vacuum tubes, if you even know what that is. If you're young, you may or may not, unless you're really into high-end audio. But they've been around many decades, as I said. I'm not quite sure when the first one was, in the 50s, perhaps in the 40s was when the first one was done, 1940, 1950. But basically, this kind of amplifier internally corrects voltage errors at the input. Today, we correct quite frequently, say, as an example, every 50 microseconds. The traditional old ones might have been once every, or about 50 times a second or so, or 20 times a second. In the process, the circuitry doesn't know what causes the voltage error. All it does is measure it. It doesn't know the cause. So because it treats all causes the same, it corrects offset drift over temperature, open loop gain, common mode rejection, power supply rejection, aging, and maybe surprisingly enough, 1 over F noise. They all get corrected. Now, at room temperature, as a downside, they do tend to increase offset current. Bias current, usually not so much, but mostly offset current gets increased at room temperature. Here's a list of zero drift op amps available today from Microchip. Probably not much to really focus on here, other than to say the performance is really good, and you'll see that we have, there it is, on this side. The gain bandwidth product covers a wide range, all the way from 80 kilohertz to 10 megahertz. And it's because we were doing these parts that we've learned as much as we have about them. There are also op amps that have low bias current. So most CMOS op amps have fairly low input bias current, but all amplifiers have to have ESD diodes. So even with CMOS, we're going to get bias currents because of the ESD diode. And because they're silicon devices, silicon diodes, you're going to have a doubling of your current every 10 degrees C or so, depending on how it's designed. Another precision component is del-sig converters. They're fairly well known these days. I've just thrown up 3 different del-sigs that we do. We do more than this. This is just a sampling. Here's a precision component that most people don't think of when we talk about precision analog. Why is that? It's because the PIC micro, or any microcontroller, Atmel, as I mentioned previously, is capable of putting digital smarts in a design and changing fundamentally the way the circuit operates or the way we interpret the results. So they provide different outputs, timers, PWMs, etc. Probably more interesting in many cases is the firmware. In firmware, we can add calibration, filtering, averaging. We can correct nonlinearities. At the beginning of my career, it was still fairly common to correct for instance, diode temperature behavior in circuits that use diodes as sensors, to have a resistor that had the same temperature profile. And they were very expensive. Today, we just simply do that in the firmware. So that's just a quick tour through the possibilities. In my opinion, here is where the meat of this course is at. This is where we need to focus to get our design. I've just talked about precision parts, but the truth is that you can buy the world's best part, but if for some reason your board design isn't quite right, or you pick the wrong components to go around it, you can get much worse performance than the datasheet will specify. And we have experience at doing that, and we've learned through experience how to avoid many of those errors. So let's begin with a very fundamental effect. Someday when you're bored and you want to break out your college physics book, you can go and look for the Seebeck Effect. This is the basic physical phenomenon that it underlies thermocouples and thermal junctions. Basically, what happens is if you have a big metal object big enough that you can force a different temperature on both ends, and you measure the voltage on both ends, you'll measure different voltages. That difference in temperature causes excitations of the atoms and all that. And physicists will explain that in much more detail. All we need to know is different temperatures, different voltages. And the other thing to mention is that different metals will show a different change at the two ends. So when we do a thermocouple, we take advantage of that. We take one type of wire, say copper, and another wire, say aluminum, just arbitrary choices. And because they have different properties, they're going to have a different voltage change from this end to that end, and therefore you'll get a different difference voltage at this end that's proportional to temperature, to a first order. And this slide talks about it. The gain or the temperature coefficient for many of the standard thermocouples is on the order of 1 to 100 microvolts per degree C. So if you're not lucky, you can get a really high temperature coefficient. And here's a plot. This is a plot of the sensitivity. In other words, how fast does voltage change with temperature? You'll notice that it's not flat like you would have with a perfectly linear response. It's somewhat curved. Thermocouples, standard thermocouples have polynomials that NIST, the National Institute of Standards and Technology here in the United States, publishes up to 9th order for some that correct the output for these nonlinearities. But for what we're going to do in printed circuit board design, we can just say they're approximately constant. So one of the big places that we have a problem in our designs, and I'm going to point to a board that I have here. You'll look at this board, and just from a standard point of view, you'll see 3 amplifiers, and then you'll see some capacitors and some resistors here. And to a first glance, you're not going to see thermocouples. Well, we're going to talk about the resistors that are on that board and what happens to them. So I have this surface mount resistor, and it's connected to 2 copper traces on the ends. And if you think about it, you go from the copper trace to the solder, to the metal on this end cap, to the thin film metal that's used to make the resistor, to the cap again back. And so if you go through, every time you change metal, you have a thermocouple. And so if my temperature is changing across the board, I have a temperature gradient. It's 0 degrees here, 0.3 degrees here. You're going to get different behaviors. And remember that difference in temperature is going to cause different behavior. So I go through the math, sum up all the errors, and at the very end, I get a net change in voltage across this resistor because these thermocouples are not at all the same temperature. And that creates a thing where I get about, according to this example, about 1 microvolt per degree C change across the ends. So that's on the order of, say, the offset voltage of a zero drift op amp. What happens when the temperature gradient is perpendicular to what we just described? What if the temperature changes in this direction? Well, it should be obvious that all the metals short out that direction and we get 0 effect. So this is direction sensitive. So that's another clue that we need. A third piece of information that we need is that different types of resistors behave differently. So I picked up some of this information. All the information in this area is from older literature, back in the day when axial leaded resistors were very common. I've added this one piece of information on a 0603 surface mount resistor just as a comparison to make it more modern. You'll notice that the tin oxide and the carbon resistors have very high coefficients. And this coefficient is the change in voltage divided by the change in temperature across the ends of the resistor. In metal film is better. Wire wound has the best coefficient, but anyone that's used wire wound resistors knows that they have major problems. They're huge. They're very inductive. They're expensive. And so this becomes attractive because its coefficient isn't too far off. But if you think about it, because this is much, much shorter than this resistor, that overcomes this because the difference between the distance between the ends of the resistors is smaller, and so therefore a smaller drop in temperature, therefore a smaller effect. So actually in the final analysis, the small surface mount resistor has the best performance of all. So I'm designing a circuit. I now know this information about potential errors on my board. What do I do about that? That's what we're going to talk about now. And to start, I'm going to start with just a simple non-inverting amplifier built off an op amp, 3 resistors. And then you notice in my layout, here are the resistors that set the feedback, R2 and R3, and here's the non-inverting input resistor. Notice I've kind of just placed them wherever. This one's vertical, horizontal, whatever was convenient at the time. What's more important is that I can associate a voltage effect with each one of those resistors. So for resistor 1, it's it goes in the Y direction, so I put a source V sub Ty, thermal in the Y direction, and I decide it's positive going up, so the end of R1 that connects to the input pin is positive, so that's how I decide which direction I put this source. And I do the same for each one of the resistors. Then I just simply do the math and grind it down, and in the end I find out that whatever the gain of this circuit minus 2 times what's in the X direction, and the gain of the circuit times what's in the Y direction is what I have. So this circuit takes whatever thermal errors I have, gains it up to the output, and I have a problem. There really isn't any cancellation. Now, traditionally, the recommendation that is given is that you put these two resistors close together, parallel, and at the same distance from the op amp. Very good advice. And I've put the feedback resistor in a convenient spot for me. So I do the same analysis, come up to the end, and I've canceled most of the error. The Y direction's gone because I put all the resistors in the X direction. But I'm still left with a residual error that at lower gains may be a problem. So what I'd recommend is that you add one more piece to your toolkit, which is you can orient this feedback resistor. Watch R3 as I flip back to the previous slide and then back to this one. You'll see that it changes direction. It points to the right here, and it points to the left on my recommended circuit. Changing that direction changes the math, and I get, in theory, 0 effect. Now, we all know that cancellation is never perfect, but this at least will give you a way of getting much closer to what you want. So let's talk about some other ideas. I'm not going to go in fine detail on these, but these are something to talk about. So let's talk about fundamentals. I don't want to start with, say, an aluminum wire and end in a copper wire, because that's going to create a thermocouple. So use the same metal everywhere. I want to use symmetry on my circuitry to balance out the effects. And I want to keep the input circuits close together, as I just mentioned. Now, idea number 2 here talks about inverting gains have the same layout as non-inverting gains. So all that means is on this layout, I can connect my signal here and the ground here, or vice versa, and I get either non-inverting and inverting, and the resistors are laid out the same. High gains. This principle is true. I can't think of a single amplifier situation I've ever met in my career, RF, microwave, high precision, low precision, whatever. This is always true. High gains as soon as possible. Another idea is, what if I have a known heat source? I can orient my resistors to be parallel to the constant temperature contour lines, and therefore no real temperature drop across the resistors. Now, I would have recommended actually laying this out with this resistor the other direction to help cancel any residual effect. When I was first measuring our zero drift op amps many years ago, I had to design a board to actually measure the offset voltage that we were producing, which was difficult because our first part, the offset was under 2 microvolts maximum. So it was a real struggle. And once I understood these principles, the idea I was able to come up with is I can take a single resistor, put 2 series resistors as a replacement, but orient them in opposite directions physically, and then the voltages subtract, and you get a single resistor equivalent that does not have a thermal effect. So this is a fairly handy trick. Well, this worked pretty good in several places I need it, but then I ran into a place where I was setting a high gain, and I needed the resistor to be very low to set the high gain. Well, I couldn't get the precision resistors I needed at that value, doing this trick. So what I did is I instead put them in parallel. And again, changing the orientation, I was able to get cancellation. Now, a caveat on this second trick is if these are 10% resistors, they're going to mismatch and you're going to get different currents and you're going to not get that good of cancellation. You need precision resistors to get really good cancellation. Another idea is this circuit that we showed a couple of times early on in the course where we do the input stage of the traditional 3 op-amp instrumentation amplifier. You'll notice that if I take this, usually it's 1 resistor here, if I take that and split it into 2 resistors, notice now that I have a symmetric circuit and then I have a non-inverting amplifier layout here and a non-inverting amplifier layout here. So I just do the same layout I did previously and just put it here and mirror it here, and I'm done. I have the cancellation I want. That's the reason I put these 2 resistors. Now I've tried many different ways to think of a clever way to do just 1 resistor instead of these 2, and I have not found the way to do that. Now, I've shown a lot of nice theory and a lot of hand waving. I've told you that this is a problem, but I wanted to be sure for myself 2 things. Number 1, is it a problem? Number 2, how big is the problem? And so I designed a board to measure this. And that is this board that we see over here that I'm pointing at right now. On this end, you see the bare copper. I put that in an anvil, a large steel anvil, as my thermal ground. And then I have a series of resistors on the back of the board here on this end, equidistant, and I put a lab supply putting a lot of power in there. I forget the number now. I think it was on the order of 5 watts, something like that. And so therefore it heats up this end of the board and you get a line source of temperature. And so therefore you get a constant gradient going this direction and very little change this direction. And then I have 2 dual op-amps here in the center with circuits built around them. So let's go back to the screen. What we see on the screen is the layout of this board. You notice these 2 dual op-amps. And I'll start at design number 1. Design number 1 had large resistors, and resistors are pointed in any which direction, and that was a bad design. I wanted to see how bad it was. And I did another design where I did them all horizontal, but not quite oriented right. Now, design number 3 still uses the large resistors, but they're pointed in the direction I want. And then the 4th, which is my best design, I use small resistors and they're pointed in the direction I want. I wanted to see whether large or small resistors made a difference. I wanted to see if pointing in different directions made a problem. And the answer is yes. The results prove that. But the result that is probably most interesting is that when I measured the good one, I had a 0603 surface mount resistor, or resistors, 3 of them. And as I measured the effect, the change in temperature across the resistor was 0.3 degrees. So my trick of heating the board created a change of 5 degrees C for every inch distance. That's a fairly high gradient. So I got 0.3 degrees C across the resistor, and I was able to measure a 1.1 microvolt change. So that produces the coefficient of 3.3 microvolts per degree C. And so this is a measured data point. This board is not available. I need to mention that. It is not available. It's internal only. I've used it to develop this information for this class, and that's the only purpose I've had. If you're really interested in it, you can shoot me an email. You can contact Microchip and ask. You'll see my name on the on some of the application notes that are in the back. Anyway, I can talk about it. So let's switch gears. We've talked about the thermocouple effect. Let's talk about some thermal response effects. I designed, let's go back to here. This board that I show here was designed to feature our instrumentation amplifier that we designed several years ago. On this board I put that instrumentation amplifier, and I also put a 2 op amp instrumentation amplifier to compare performance. And you'll see in the slides that it talks about that. And this is an application with an RTD put into a Wheatstone bridge. And I used this particular PIC microcontroller to do all the conversion and the firmware smarts. So here's a representation of the layout. You have the A to D on the back side in the PIC micro. You have second instrumentation amplifier with these 2 op amps here, and then you have the first instrumentation amplifier, which is the dedicated instrumentation amplifier. This is an interesting thing to do. I was able to play with it, try different things. A couple of the key results that I found was that this PIC micro on the back had about a 10 degrees C temperature rise. So it's a heat source. And I put it in the center so it kind of has a very small gradient, as small as I can get for the circuit. So that's something to consider. Other components can be heat sources. The other thing I did, if we'll come back to the board to explain this, on this corner of the board, I have my RTD sensor. So I took a piece of paper here so I could separate the RTD sensor from the rest of the board. Sorry, I shouldn't have touched. Is that good? To separate it. And then I took my freeze spray can and I sprayed it on the side of the paper that the sensor was on so that I didn't affect the other components on the board. And this is the measured result from that experiment. I measured for 120 seconds, and the initial change was minus 85 degrees C. Now I'm plotting the magnitude of the temperature change here because Excel doesn't like plotting negative numbers on their log plots. So I'm plotting the magnitude. So minus 85 degrees C, and then over the first 10, 15 seconds, it comes down pretty fast, and then it goes down slow. So you basically have 2 slopes on this semi-log plot. Now, fortunately for me, my college physics professor covered this in one of our labs. He told us how to handle it. This is basically 2 time constants that get, and the effects get added. And so you can fit to that, and you find the first time constant is 4 seconds, 4.2 seconds. The second time constant is 94 seconds. So what on this board, if we go back and look at the board, why would we have 2 time constants? Well, it's very simple. You have this incredibly small RTD. My pen's pointing to it, but you probably can't see it very well. And then you have this big board that explains the bigger time constant. So the RTD is this short time constant, and the board's the long time constant. So this is a principle that you need to be aware of. If I took something bigger, say my laptop, its time constant is going to be many minutes long. If I have a measurement rack system, you know, TV shows showing NORAD, you'll see a wall of just filled with instrumentation. Or if you see NASA, when they do space shots, you'll sometimes see their communication racks in the background, floor to ceiling, wall to wall. They're going to have time constants on the order of days, if not weeks. You need to be aware of that. When I started my career, a lot of the equipment that I used was built in the 60s. And you had to turn on the equipment for 24 hours before you could start taking measurements, because before then the thermal effects would cause the results to wander a lot. And it was a real problem. Today we use microcontrollers to automatically calibrate all that out. So, we've learned how to do printed circuit boards. What does it do for applications? Well, the one I'm most familiar with is probably doing data sheet, data collection, so we can present our parts to you. So I'm going to talk about what we saw on a part that we originally released before we understood this well and before we had all the equipment and techniques in place. And then we took some newer data based on this information in this class to improve the situation. So here's the original data we took, 20 different op amps. We went from minus 40 degrees C to plus 125. We took, the reason this is kind of piecewise linear is we took data at 4 temperatures, minus 40, 25, 85, and 125. You'll notice what I call a bow tie effect. Here, near room temperature, it's tight, and at the temperature extremes, the data is a lot poorer. On the right, you'll see the same data, the same scale, taken with much better setup, where we control the temperatures much better, the temperature gradients, and we do much more precise measurements. And you'll see that those results are much more believable and much better. So the original offset data, this is the linear temperature coefficient on a scale of plus or minus 50, which was the spec. You'll notice that we had measurements as much as 20 nanovolts per degree C. The new data on the right has a different scale. This is plus or minus 50. That one's on a scale of plus or minus 10 on the x-axis. And you'll see the worst case measurement was 5 nanovolts per degree C. It's basically 5 times better. And the component that we're talking about, the MCP6V27, did not change. It's the same component. What changed was our measurement technique. And here's the quadratic temperature coefficient, same type of thing. In this case, it was 20 times better. So we benefited from that. You can benefit too. Before we leave this topic of voltage errors on printed circuit boards, I do need to mention that there are other effects that you need to be familiar with. Crosstalk is obviously a problem that all of us are very familiar. You also have DC crosstalk where, for instance, you have a power driver on one side of your board that draws a lot of current from the power supply, and you have a sensitive high gain precision circuit on the other side of your board. The current on one end of the board can affect the accuracy of your sensitive circuit on the other end of the board. So that's a DC crosstalk situation. Nonlinearities. I've found that this is not understood very well. So I'm going to talk about this in a little detail. I'm going to go to the board and I'm going to put up an equation that all of us learned in college for calculus and then proceeded to forget after college. But I'm bringing it back to mind. If you square the cosine, you get the sum of a half and half of the cosine of the double angle. Well, basically, this square is the nonlinearity, and out of it I get a DC term and a second harmonic term. So that's an example of a nonlinearity that will cause a DC shift. The more common nonlinearity that causes a problem are the ESD diodes at the input of all op amps or any type of amplifier. because we have a diode at the input, and by the way, those diodes are incredibly fast. They have to deal with ESD events that are on the order of a nanosecond in duration. They're very fast, they're very nonlinear, and they can conduct a lot of current. So what that does to an amplifier is if I have radio frequency interference, some kind of RF crosstalk, that'll be rectified by those diodes, and that rectification causes a DC offset to be added to the amplifier. I have seen as much as around 600 or 800 millivolts shift in the offset in particular applications. So that's something to be aware of. Oscillations, most of the components we've talked about, oscillations usually aren't too big a problem. It's not like the RF world. In the RF world, the standard joke is that all amplifiers oscillate and all oscillators amplify. And it's a standard joke because it happens most of the time. That's not the case in audio frequency type applications, or maybe up into the 1 to 10 megahertz type applications. That's not so frequent. But it is a potential source of problems. If your amplifier is oscillating, none of your measurements mean anything. None of them. Any DC level, any quiescent current draw, anything you measure is not right. It's wrong. You have to get rid of the oscillation, then you can measure. Triboelectric effect. If you look up the triboelectric effect on the internet, you'll probably get an explanation about how this is static electricity, and they'll talk about the birthday party trick of rubbing a balloon in your hair and having your hair stand up. Yes, that's true. That is the triboelectric effect. The way it applies to what we're talking about may not intuitively seem like the same thing, but it is. I'll take this cable, this USB cable, as an example. If you look at it, you have the insulator on the outside. We know that we have a shielded, braided shield on inside, and then some more insulation, then a center conductor, just like a coax in many ways. So, and this will have multiple conductors because it's a USB cable. But that's the basic situation. So I take this cable and I make it form a circle. And as I get that circle tighter and tighter and tighter, eventually I'm going to get it so tight that the metal and the insulation are going to separate and cause a gap. As soon as you have that gap, you start to form static charge collection on the insulator. And that's the triboelectric effect that I'm talking about. That is the problem. As soon as you have a collection of charges somewhere on this cable, that causes a DC offset voltage. So the simple thing to take away is if you have, like I used years ago, I had a technician that just loved pretty wiring. And so when he wired our boards to our equipment, he would take it and he would literally take my coax cable and turn them at right angles, literally right angles. He'd bend them so sharp that they looked square and caused us no ends of grief. Not only did it cause this effect, but it also damaged that and created a reflection at microwave frequencies. It was just really bad. So the message is that can be a problem. Another effect is the piezoelectric effect. When I started, it was more common to call it the microphonic effect. Basically, if I take a board and I tap on it, every ceramic capacitor on the board that's non-ferroelectric, in other words, it's one of the larger capacitors, is going to cause a voltage spike. Dielectric absorption, you can look this up on the internet for the details. That can cause DC level shifts too. For instance, if you have a track and hold and you're using a capacitor and you don't clock very often, this can be a big effect. Switched inputs, Yeah, switching can cause problems. Another problem that gets confused sometimes is that all devices generate random noise. I'm not talking about noise in the sense of crosstalk or unwanted signals. I'm talking about the inherent thermal noise and shot noise effects, etc., that cause random behavior. That can appear as a wandering offset, an offset that changes and it doesn't make sense. Another thing to talk about is contact potential. Back in the days of vacuum tubes, this was well understood because if you have two different metal objects in there just touching, you get what's called the work potential between them, and you'll get a small voltage shift. So where we ran into it was when we were characterizing our first zero drift op amps. For convenience, we were putting the op amps in a pin socket, and then we'd measure the offset. And we were having problems getting to where simulations said we should be. And it wasn't until we bit the bullet, we decided, yeah, we got to do it. And we actually soldered the parts onto the board that we got rid of the last 1 or 2 microvolts of error. And that last 1 or 2 microvolts of error was due to this effect. So if you're just putting say you're prototyping a part and you just do this, be aware that you're adding some error if you don't solder it down. Component selection, smaller resistors are better, etc. Circuit design point of view, as we all know, if your performance isn't good enough, you can always buy a better part, up to a point. Then, of course, printed circuit board design. Then to talk about the random noise effect a little bit more, I threw in this slide just to make it clear. My experience is that among analog designers, not many of us out there that are pure analog. Of us, maybe 10% of us know how to do the traditional noise analysis. 90% of the analog engineers out there quite simply know they have 2 dials to do. You can change the level of the screen line which represents your part by buying a different part, and you can change the bandwidth to reduce the noise. You can dial those 2 knobs to where you need them and you're done. And that's all they need to know. Not many of us have to get into the detailed noise analysis. So when we do signal filtering, and by the way, when we're in firmware and averaging or doing a FIR filter, we're doing signal filtering. This helps reject crosstalk that's out at high frequency. Doesn't reject crosstalk that's in band. It helps reduce random noise, and here's a very important one. It helps prevent A to D aliasing problems. Now let's talk about low current errors. This is a little bit more difficult thing to achieve. There are some practical problems, and we're going to start out talking about surface leakage. In other words, on the surface of the board. And the number one problem is contamination. No matter what you do, your board's going to get contaminated in one way or another. So what are the common problems? Humidity. And by the way, when humidity condenses onto the board and forms puddles of water or moisture tracks, it also collects other chemicals that may be in the environment and deposits them on the board. That's a problem. Another problem is dust. Dust collects. What's not well known is that any electronic component, say my laptop, it's exposed to the output air because the fan blows air out. Because I have voltages in here, I have voltage gradients in the air, and those voltage gradients attract metallic dust. Dust that has a higher metal content which conducts more. It doesn't attract pure silicates, standard sand, for instance. It attracts the type of dust that's going to cause a problem for your electronic system. So I started way back when as an electronics technician, and I learned early on the first thing you do when you open up a piece of equipment that you want to repair is you get out this vacuum cleaner, by the way, not your wife's vacuum cleaner. You get out a vacuum cleaner and you carefully vacuum out all the dust. And that clears up a fair number of problems, and at the same time, it makes it easier for you to find everything that's going on. You can see better. Chemical residues. In manufacturing, we get residues, solder flux, all kinds of other chemicals. And so we're all familiar with flux removers. I'm here to tell you that the standard flux removers can also be a problem. They'll take the flux off the board, but they will leave a residue that at the precision levels we're talking about is a real problem. That was another contributor to our errors when we're measuring our op amps. We found that if we left the board with just the standard solder flux remover residue there, that we would get a couple of microvolt error. And our technician found that if he used Windex as the final clean, we were able to get where we needed to be. So our standard flow now is do the standard printed circuit board build and clean and all that, and then go and use Windex to clean it one more time. You may find another final cleaner that you like better, but that's the one we've ended up with. And I had a customer point out one way to model this type of problem, the surface leakage, in your circuit diagram is to model them as just parallel resistors that are fairly high. And this shows different levels that you might want to think about, something on that order. And so in an actual circuit, I have this simple amplifier, input current source goes into a resistor, amplifies it out. Well, every voltage here causes a leakage current that goes to the sensitive input, this high impedance input, and it can be modeled as a resistor going to that node. So when you understand this, then you understand the standard traditional technique for combating this problem, which is to put a guard ring on your board. And what that does is any of these potential problems go to the guard ring, conduct to the guard ring, and in this case I'm driving the guard ring with the output voltage pin of this amplifier, so all those currents sink into this output pin and they don't go to the sensitive node. So you can cut your leakage currents by a factor of 1,000 or so if you do this right. Now there are a couple of things to be careful when you do this. You have to remove the solder mask on top of these traces. It has to be bare metal for it to work. It's not going to conduct through the solder mask. The solder mask is a fairly good resistor. The other thing is if any of these components are through hole, you'll need the guard ring on top and bottom surfaces. You'll have to guard ring both surfaces. And there's an example layout on the top right of one way it might be done. And in order to do guard rings, as those of us that have tried to do it, you have to use older, large pitch type of packages to make it happen. Some of the fine pitch packages you can buy today, you simply cannot put a guard ring between the pins. They're too small and too closely spaced together. Another type of leakage in boards is what's called bulk leakage. In other words, the current flows inside the board, not on the surface. So it'll go through the dielectric material, such as FR4, which is very common. Now, by the way, this dielectric, if it gets wet, say it gets immersed in water, and then you try to use it, that water contained inside the dielectric changes the resistivity a lot. You can get dielectric materials that have strong resistance to being wetted, and etc., but you do pay for them. And again, you can model with parasitic resistances to model what's happening inside the board. And my experience is this effect tends to be like on the order of 1,000 times smaller than the surface effect. Your experience may be a bit different, but usually the bulk effect is not as large. And so this goes through some, these slides go through some ways that we can handle this. So for instance, I have a printed circuit board and I have traces going along the board that are on top of each other. Here's a top view, end view, and a side view. You'll notice that you have ample area for the leakage currents to go here. Well, if I run one trace on one end of the board and the other trace on the bottom on the other end, now I have a much greater distance that I have to have the leakage currents travel through, and so I'm going to have a much higher resistance. So that's one idea, just simple physical separation. Another way to handle this is to run my traces in perpendicular directions so that basically the only area that it really leaks is here at the crossover. That'll greatly reduce the effect, just like it reduces capacitive coupling between two traces on a printed circuit board. Another trick is to guard ring. And so if I guard ring, then any leakage currents tend to go to the guard ring instead of to the victim. Another idea is I can put a ground region or a constant voltage region internal to the board, or I guess it could be on the surface too, that covers a fair area. So any leakage currents from here would tend to go to this ground plane, and then finally a little bit will end up here. But if you think about it, this acts like a multi-lump attenuator, because no matter where you're at here, every time you're going to, every little increment of distance in the x direction, you're going to get more current going down into that ground plane. So since you have multiple lumps, you get much greater attenuation. The attenuation goes up or exponentially, I should say. Yeah, we can use coatings for moisture control. Coatings bring their own problems. If you've ever used them, you're aware of them. There's something to look at. Traditionally, sensitive nodes have been isolated from the printed circuit board. You look at some of the really old literature, they'll talk about Teflon standoffs today. That's kind of hard to sell. It's very expensive, and you have your environmental concerns. What's more common now is to cut out an area on the board so that a sensitive node does not touch the board. That's probably good enough. Again, you can use cutouts and different dielectrics for bulk leakage. And that pretty much covers the class. I'd like to summarize and then just comment a little bit about what comes after the class in the PDF file. So first of all, we have the high precision circuit material that we covered. Talked about how it's going more mixed signal, less analog, pure analog. Many topology you can use in the accuracy. Now the precision parts we talked about, zero drift op amps, ADCs, and then some help from the microcontrollers. And probably the bigger issue that has been covered by this class is on the printed circuit board, the different error sources and how to minimize them. Now, this is all material after the class. This is not officially after the class. I just want to comment. I show some references, application notes, data sheets, and demo boards that are related to this class. In this appendix, Appendix B, I show a comparison of effects, different sensors and their effect, different types of op-amps and what error level they have, delta converters error levels, resistors, capacitors, printed circuit board. And these are just order of magnitude numbers. If you're not familiar with that type of error, it may give you a place to start. And then I go through the circuits in detail. Thank you for listening to me. This class covers a lot of material. I recognize that, but this is material that is incredibly difficult to find elsewhere, and some of it is not found elsewhere. So I appreciate your time and your effort in learning, and I wish you luck and good experiences in your designs when you're doing high precision design. Thank you.